Denise, beginning at rest, heads down the frictionless hill shown below. At the bottom, a circular arc carries her through a 90-degree turn, and then she launches off a 3-meter high ramp. How far horizontally does she land from the end of the ramp? Okay, so we're looking for this distance that she travels from the end of the ramp to where she lands over here. This is what we're looking for, D. Okay, so in this question we have two parts. In the first part, she's traveling from the top of the ramp to this point over here. Okay, there's no mention in the question about friction, and there's no other external forces acting on the system. So we can say energy is conserved. So that means the total energy she has at the top of the ramp is equal to the total energy she has at this final position over here. Okay, so this is initial position and then final position. So that's the first part. I'm going to write that out. Part A. So that would be transfer of energy. Once we find out what her velocity is at the final position over there, we can then figure out how far she's going to land by treating that as a projectile. Okay, so that would be part B. Projectile. Okay, so let's start with part A. So the total energy that she has initially is equal to her total energy final. So what kind of energy does she have at the beginning? Well, let's define where we want to have our zero height reference position. Let's say at the very bottom our height is 0. So initially she has a height. She's beginning at rest. So that means she has no kinetic energy. Nothing is rotating here, so we don't need to worry about any type of rotational kinetic energy in this problem. She starts off with a height. There's no spring in the question, so there's no elastic potential energy. So initially, she just has gravitational potential energy because she has a height. In the end, she still has a height because she's up here 3 meters off the ground. So she still has gravitational potential energy, but she's also going to be moving with a velocity. So that's kinetic energy. Okay, so let's put in the formula. So I have mgh initial equals mgh final plus 1/2 mv squared. Okay, so we're going to try to find her velocity at the end when she's about to become a projectile. So we'll solve for her final velocity. Well, notice that her mass is the same everywhere here, so I can just divide it out of all the terms, so it's gone. And now I can solve for v final. So I'll bring my ghi minus ghf equals 1/2 v final squared. I'll multiply everything by 2. So now I have 2ghi minus 2ghf, and then I'll square root. 2gh initial minus 2ghf. Really, we should be putting a plus or minus in front of the square root. Now I can plug in all my numbers. So I have 2, g is 9.8, h initial is her initial height when she's at the very top of that ramp, 25 meters, minus 2, g is still 9.8, and h final is her final height when she's at the bottom of that ramp, about to become a projectile, so that's 3 meters. I'm going to type all of this into my calculator. And I get plus or minus 20.76536 meters per second. Okay, so the plus or minus is there just because to get rid of a squared, I have to plus or minus square root. But we know that her velocity is positive because she's moving in that forward direction. So I'm going to disregard that minus that's there, and it's just positive. Okay, so now we're trying to find out how far she lands horizontally from the end of the ramp. So I'm moving on to part B, which is my projectile. And so for this part, I'm just going to draw a little graph here. So I'm going to treat this like it's my y-axis. And over here, this is my x-axis. And the point at which she lands, which I call D, I'm going to label that on my x-axis. So that would be right here. This is my D. This is my initial velocity, v initial, and this angle is her launch angle, which is 30 degrees in the question. Okay, so it's telling us in the question. She's launching at 30 degrees over here. Okay, so the first thing that we do for our projectile motion is we draw the graph just like we did there, where we draw out or sketch out what her motion would look like. So we're done that. The next thing we do is we draw a table that has x and y, and on the side we have all of the kinematic variables, s initial, s final, v initial, and a. So S initial is referring to her initial position, which is now over here. So notice that our initial position is our final position from part A. So this is now our initial position, and our final position is when she lands. Okay, so what is that point there? The x-coordinate of the point is 0, and the y-coordinate is 3. So it would be 0, 3. When she lands, her x-coordinate is d, and her y-coordinate is 0. Now her v initial. Our v initial is the v final we got from part A. So it's 20.76536 meters per second. We need to find the x and y components of that. When we're finding the x component, that's the adjacent side. So we're going to use cos. 20.76536 cos of the angle 30. And the y component, 20.76536 sine, since it's the opposite side, the y component of the angle 30. Okay, notice the x component and the y component are both positive because the vector is pointing to the right and upwards. For all projectile motion questions, the acceleration in the x component of that is 0, and the y component of the acceleration is negative 9.8. Okay, because we're assuming that to the right and up is positive. Now that we've drawn our table, we're going to pick the column that has the most information. So that would be the y column. And we're going to solve for time using a kinematic equation. We're going to use this kinematic equation. S final equals S initial plus V initial delta t plus 1/2 A delta t squared. Okay, so I'm going to plug in my numbers. S final is 0 equals S initial 3 plus V initial, which is 20.76536 sine of 30 delta t plus 1/2 negative 9.8 delta t squared. Okay, so I can plug this into a quadratic formula. So my A in the formula is right here, negative 4.9. When I multiply 1/2 times negative 9.8, my B is the middle term, 20.76536 sine of 30, and my C is 3. Okay, I'm going to just type all of this into my calculator. And when I solve for delta t, I get negative 0.2576 and positive 2.3765. All right, and this is in seconds. Now time can't be negative, so this first answer is inadmissible. So now we have our time. Now that's not what the question's asking for though, it's asking for a d. So we're going to take that time and put it in the x direction here. So this is my delta t that I just got, 2.3765 seconds. That time is in the x and in the y direction because time is not a vector, it's a scalar. So we get the same value in both of those columns. Now we can solve for d. So now I'm moving on to the x direction. So first I'm going to just write y direction here. And now I'm moving on to the x direction. So I'm using only the information in the x column, and I'm going to use that same kinematic formula. SF equals S initial plus V initial delta t plus 1/2 A delta t squared. And I can plug everything that I know. So my SF is D, that's what I'm looking for. My S initial is 0. My V initial is 20.76536 cos of 30. Delta t is 2.3765, My a is 0, so this whole term goes away. So now when I plug all of that in, I get 42.7, and that's my x direction, that's my distance traveled, so it would be in meters. So let's go back to the question and check our significant figures. So you can see we have 3 significant figures, 3 significant figures, and 3 significant figures. So our answer should also have 3 significant figures. Thanks for watching.